In this video, we are going to learn about relations. What is relation? A relation R on a set A is a subset of A cross A, meaning it has two elements in A. So, we say that if element A, B is in relation R, we would write A R B, which means A is related to B. For instance, if A is a set containing 1, 2, 3, B is a set containing A, B, C, and given a relation R containing A, B where A is less than B, A is an element from set A and B is an element from set B. Hence, we know that 1 is related to B, 1 is related to C, and 2 is related to C. There are 6 different properties of relations, which are reflexive, irreflexive, symmetric, asymmetric, antisymmetric, and transitive. First, let's look at reflexive. A reflexive relation is a relation where A, is in the relation for all of the A's, which means A is always related to itself by the relation. The question is, how to determine whether the following are reflexive relations? If we are entering a value into R, is it true that all A, is in the relations? Hence, R1 and R2 are reflexive as they have equal sign, while the others are irreflexive. A relation is said to be irreflexive if A, is not in the relation for all of the A's. Next, we are going to explore symmetric relations. A relation R is symmetric if B, A belongs to R whenever A, B belongs to R, which means whenever there's A, B, there must be B, A. So, which of these relations are symmetric? We can see that R1 and R4 are symmetric, whereas R2 and R3 are asymmetric. What is asymmetric? A relation is asymmetric if B, A does not belong to R whenever A, B belongs to R, which means whenever there's A, B, there can't be B, A. The following property is antisymmetric. An antisymmetric relation is a relation if A and B are elements of set A and both A, B and B, A belong to the relation. Then it implies that A is equals to B. To be simple, whenever there is A, B, there can't be B, A unless A is equals to B. In the example, R4 is not antisymmetric. To see that, we use an example of 0, 2 and 2, 0. Both of them are less than 3. But does that imply that 0 is equals to 2? No. So R4 is not antisymmetric. The last property is transitive. A relation R is transitive if whenever A, B is an element of R and B, C is also an element of R, then A, C is an element of R for all the values. From the examples, we can see that R1, R2, and R3 is transitive as these relations contain A, B, B, C, and A, C.
Part 2. Representations. All you need to know is Boolean matrices and digraphs.
There are two ways to represent relations, which are 0-1 matrices and directed graph, or known as digraph. Relation can be represented by 0-1 matrix MR. If Aibj is an element of relation R, Mij equals to 1, else Mij equals to 0. Let's look at the example 1. A equals to A1, A2, and A3, while B equals to B1, B2, and B3. R is a relation from A to B. R equals to A1, B3, and A3, B2. Let the elements of A become the rows and elements of B becomes the columns. The matrix MR is like this. A1. Let the elements of A become the rows and elements of B becomes the columns. The matrix MR is like this. There are some properties that are only applicable on square matrices. The first property is reflexive relation. A relation is a reflexive relation if all the diagonal elements of the matrix is 1. Here is the example. And the second property is symmetric relation. A relation is a symmetric relation if the matrix is a symmetric matrix. A symmetric matrix is a matrix which is equal to its transpose, which is MR equals to MRT. For example, 1 0 1 0 1 0 1 0 0 is a symmetric matrix. There are two Boolean expressions which are Boolean OR and Boolean AND. For example, these are matrix A and matrix B. For Boolean OR, 1 or 0 equals to 1, and for Boolean AND, 1 and 0 equals to 1. Now, how to represent composite of two relations? Let's say relation A is represented by matrix MA, while relation B is represented by matrix B. Composite of BA is the Boolean product of MA and MB. To show in graphical way, relation A maps A to 1 while relation B maps 1 to D. Therefore, composite BA maps A to D. For powers of relation, the power of relation can be the power of the matrix of the relation. For example, matrix of R square equals to the square of MR, and it is equals to MR times MR. Just apply the multiplication method of matrix to get the answer. The 0-1 matrix representation part is over, and we move on to digraphs. There are a set of vertices and a set of edges in digraph. An edge is a pair of connected vertices. For edge AB, A is the initial vertex while B is the terminal vertex. For example, this is a digraph with B equals to ABC and E equals to AB, AC, BC, and CC. The relation is shown with arrow. We notice that there is an edge from C to C. This type of edge is called as a loop. There is one important thing while applying digraph. The relation must be one-to-one correspondence. One-to-one correspondence means each element of one set is paired with exactly one element of the other set, not 2 and not 3, exactly 1. And here is the example of one-to-one correspondence.
Hello, in this video we will learn about relational database and equivalence relations. N-ary relations A1, A2 till AN B sets. The relations of this set is a subset of A1 times A2 times AN, where A1, A2 till AN are domains and N is a degree. A relation is a data set that is organized into rows and columns as shown in the example below. The number of columns is 6, thus the degree of this table is also 6. The table below is a relation table which represents complete unit of information. Each row of complete set is called n tuples or records. Each columns are called fields that are entries to n tuples. Primary key is used to identify domain of relation whose value uniquely, which is not repeated. Let's take this table as an example. There is more than one field that are unique, metric ID, name and subject ID. But metric ID is the most suitable to be a primary key. A composite key is a combination of set of domain that is unique. Based on the table, the possible keys that can combine is name plus surname, which identify uniquely. Thus, it's a composite key. Operation on n-ary relation. Projection. Let's see the tuple below of a student. If a projection of 2, 4 is applied to the record, other information are removed from the record. Thus, the answer is Muzamil and Alkm 400. Scan is joined where two tables are combined into one if they share some identical fields. From below table, it can be seen that both tables share a field called subject ID. Since table 1 has 6 fields and table 2 has 3, the relation of J1 has 6 plus 3 minus 1, that is 8 fields. Now, moving on to equivalence relation, which is simply a relation that is reflexive, symmetric, and transitive. And we say that two elements that are related by an equivalence relation are called equivalent and denoted as shown below. Symmetric is A equivalent to B whenever B is equivalent to A. Transitive, where if A and B are equivalent and B and C are equivalent, then A and C are also equivalent. Reflexive is every element is equivalent to itself. Let R be the relation of the set of real numbers such that A relation B if and only if A minus B is an integer. Is this an equivalence relation? Number 1. Reflective. A relation A must be A minus A where the number should be integer. A minus A is equals to 0 where it is an integer. Thus, it is reflective. Number 2. Symmetric. A relation B must be equivalent to B relation A, where A minus B is equals to C and B minus A is equals to negative C. Since both have C with different sign, thus it is symmetric. Number 3. Transitive. A relation B and B relation C is equivalent to A relation C, must be an integer. Since A relation B and B relation C is an integer, thus A relation C is also an integer. Thus, it is transitive. Equivalent classes, where the set of all elements equivalent to an element A of A through equivalent relation R is called an equivalence class A1, denoted as below. From the question and answer below, we can simplify that the element of set A, which is A and negative A, is integer and the pattern is repeated. Partition. A partition of a set S is a collection of disjoint, non-empty subsets that have S as their union, where it means there must be no empty sets, there must be no overlap, and all elements are included. The partition show odd number and even number that is denoted by A1 and A2. From the question and options available, the answer is P2 because there is no empty set, there is no overlaps, mean there is no repetition, and all elements are included. The properties. If R is an equivalence relation on a set S, then R can form a partition of S. Conversely, a partition of S can also form equivalence relation R.